Hi there, neighbor. It's a beautiful day in the neighborhood today, isn't it? Today, on our show, we're going to be learning about wide channel flows. And what a better place to be doing this than in Tippecanoe County, where the Wabash River runs through our back door. So the unique thing about wide channels is that you can assume that the hydraulic radius is the same as the uniform depth. So we have a problem here where we're going to look at the Wabash River and look at the backwater profile classification and some other characteristics using Manning's equation and other values that we've been given. So first off, our givens, our B value is equal to 400 feet. Our slope is equal to 0.0001, and our Q value, which is the flow rate, is equal to 6,200 cubic feet per second. These three values we got off of the USGS website for the Wabash River. N is for Manning's equation, and it comes from table 10.1. It's actually from the classification that's for major natural channels and major rivers. Y is 5.2. It's also from the USGS website. That's the actual depth of the river. This Q value here is big Q over B, and that's equal to 15.5 feet squared per second. G is the gravity due to acceleration due to gravity, and it's equal to 32.2 feet per second squared. And then kappa is also in Manning's equation, and it is 1.49 for the English units. Now again, we're assuming that this is a wide rectangular channel. Alright, for part 3A, we're asked to determine the expected uniform depth, Y sub n. To do this, we're going to use Manning's equation, which is listed right here. In order to do that, we're going to need to substitute some values in. So first off, we know that V is equal to Q over A, which is equal to Q over BYN. So we can substitute that in for V here. RH is equal to YN because it's a wide channel. Now to explain this a little bit further, we know that RH is equal to A over P, which P is a wetted perimeter, which can be seen right over here, using this diagram of a cross-section of the wide channel. So we know that as the width gets so much bigger, this y term here goes to 0, and then you pretty much get By over B. This cancels out also and gives you Yn. So we substitute Yn in for RH. After rearranging, or after plugging in all the values we know, we have Q over By equals kappa, which is from the English units, over N, which is Manning's N, times Y to the 2/3 times slope to the 1/2. This equation rearranged for Y is as follows here. And then after plugging in all the values that we were given in the beginning, your uniform depth for these USGS values is 8.65 feet. Alright, in part 3B, we're asked to classify the river / flow rate as mild or steep. So to do this, we need to first find the critical depth of the river. This critical depth can be found by this equation here. YC equals Q squared, little q squared, over G, all to the 1/3 power. After solving that, you find out that your YC value is equal to 1.94 feet. So in order to classify this river as mild or steep, we need to look at the uniform depth value and the critical depth value. The uniform depth value we found in the last part is 8.65, and the critical depth value is 1.954. So we can see that the uniform depth is greater than the critical depth, and therefore the river will be classified as mild, according to the backwater profile classification table. Alright, in part 3 we're asked to determine the backwater profile classification. In order to do this, we need to take the uniform depth value, the actual depth value, and the critical depth value, and compare them all. And as we can see from the values that we have, the uniform depth is greater than the actual depth, which is greater than the critical depth. And then by looking at the backwater profile classification table, we can determine that the profile is actually M2.
So here is our backwater profile classification chart, and this is what we use to classify the backwater profile as mild or steep, and also within the mild category, which we determine in Part 3B, as M2, which we determine in Part 3C. You can see that the mild slope is because the uniform depth is larger than the critical depth, and then between M1, M2, and M3, which Matt's hand is covering right now, you can you can see that it would be M2 because our actual depth was between the uniform depth and the critical depth, which you see on M2. The line here represents the changing depth of the actual river flow. Here's the uniform depth, and here's the critical depth.
This is our Y value, the depth of the river. We started at 5.2, and then every time we're going to add delta Y to it, all the way down until it gets to YC. This is our X value, which is constantly incremented in 10 feet. Area is the width of the channel times the height of the water, our Y value. RH is just area over the wetted perimeter. Volume is our flow rate over area. Our friction slope is Q over kappa over N times the area times hydraulic radius to the 2/3 power squared. The Freud number is velocity over the square root of G over Y, and dy dx is our initial slope minus the friction slope all over 1 minus Freud number squared. And our dy is dy dx times delta x. And then you take that and add it back to your y and continue all the way to yc. So this is the backwater profile for the Wabash River that we've calculated. It starts at our initial y of 5.2. And as it goes downstream, it's slowly decreasing in y until it finally hits the critical y value, and then it's going to level off, which is about 2,200 feet. As you can clearly see, it is of the M2 profile. So as you've seen before, the equations are set up in the table and repeated over and over again until our y equals our yc value. Which is 2,170 feet downstream, and then it levels off to 1.9.
I just needed to bring this public service announcement to everyone's attention that the numbers that we're using in this problem may vary from day to day from the USGS website. The Wabash is usually around 6 feet or so, typically, and lately, he's a good man. Lately it's been closer to, I think, 18 feet because of all the rainfall we've had. So these numbers are going to change often, but this is just an approximation for the values that we used. You should still get the same slope or the same type slope classification for your problem, and your overall result should be similar to what we got here. So good luck, and everybody, if you actually watch this, good luck on the final.
One moment, please. Technical difficulties.
So what's unique about wide channel flows is that you can assume that I have no clue.
Hey guys, I am the guy who was running the camera. I know you're probably all thinking, I'm glad he was running the camera because I didn't want to look at his face full time. They smell like garlic. What you looking at? What you looking at?
you know there's a charger here?
What's that?
A charger?
A charger?
A laptop charger?
I mean, we haven't been here that long, but I haven't seen one. No.
We look at the uniform depth value and the Y critical value. The uniform or the critical depth value. Yeah.
Wow. Wow. Crap. Dang it. I couldn't be a cameraman in real life. I'd laugh at people.